Hi everyone. So the aim of the lecture of today is just to introduce some topics and papers so that you can dig into by yourself. So we will consider um, five points. So there's a typo here. So first, it's about a paper which deals with the dendrite architecture and the mitochondria distribution. So that's a very interesting article for this course, which deals with networks, dynamical systems. Uh, yeah, because you have the network topology with the dendrites, and you have some dynamical systems, and that's in the brain. So that's made from people for a neuroscience lab, biological lab. So yeah, it fits very well into this course. Um, Another topic is well, so this is more math, theoretical physics, nonlinear physics. But maybe you didn't have a chance to study these things. So um, it's a proposition. So it's the idea is to start with, for example, the book of Strogatz, where you have a definition of Lyapunov exponents and try to do numerical simulations with chaotic systems. Then the idea is to the point three deals with strange attractors, and in particular, we will propose, um, um, in fact, some papers from um, David Ruel, Lei Song-Yung, and I would like to add a word here. It's Hopf bifurcation. Uh, you have a, I think we saw a lot of things with Hopf bifurcation, and here I will present also an article which connects these things. All right, the fourth paper is about a paper where you find some interesting oscillations in 3D slow fast systems, and how is this connected to a specific PDEs. And the last point, if you want to, is so when you deal with some PDEs of the point four, stationary solutions are given by elliptic equations. And so an interesting tool that you can use to prove existence of solutions for elliptic equations, for elliptic nonlinear equations, is the topological degree. And I will also give a reference with other techniques to prove that, right? So let's move on. And this is the first point. So you can find the paper on bioRxiv. And this is a team from Columbia University. And so so I picked up some interesting quotes from their paper. So what they studied is, again, the Drosophila. And here it's the visual system. And so it's well detailed in the paper what kind of neurons they studied. So you can go into that things, and yeah, so they show that mitochondria make up a dynamic system at steady state with significant transport of individual mitochondria within a stable global pattern. So what does it mean? We will see. So in fact, they present, again, this is a quote from their paper. We present a mathematical model in which four simple scaling rules enable the robust self-organization of the mitochondrial population. And of course, one of the interesting points is that this model is tested with real experiments. So those are the rules. Uh, okay, so you have this kind of yeah. So you have different rates in their model, and so that's the four assumptions that they use. So uh, you have to, if you want, you can go into more details. Of course, that's the point. But so scaling of mitochondrial transport with dendrite radius. So you have some parameter, and it's given. So you have the radius. You have to choose a beta, but this is so they relate this parameter with the dynamics. Okay, so it's a transport equation. So this will stop the movement of mitochondria. So you have to check that on the paper. I just want to give some ideas to appeal to the study of this paper. Next, of course, it's based on the topology of the network. So you have the three. So the dendrites of neurons form trees. So what's the rules for those trees? And actually, this is the point two, is how mitochondria will move uh, on the different, at the bifurcation, how the mitochondria will move. So you have two roads. What road are you choosing? And so they use some rule that's written here. So for example, if the dendrite splits in two parts, so you can say that the parent has two daughters, one and two. So how, which one, which one do you choose, one or two? And so the point two says that the rule is given by this equation: P1 divided by P2 equals R1 square divided by R2 square. All right, then you have the another parameter is the radius of um, the branches of the neurons, and this is given by this law. And so typical values are 3 divided by 2. They call it Rolle's law. Alpha equals 3, Murray's law, and alpha equals 2, Da Vinci scale. Okay, and finally, honestly, I didn't get so much into the last part, but uh, so you have also, it's again linked with the trunk thickness between sisters, so because you have a parent and daughters. Um, so there's also some scaling here. Honestly, I didn't get so much into the point four. I let you do that if you are interested. So uh, then the last thing that I wanted to present with this paper, oh, yeah, this is this equation. Uh, so the mitochondria move, and they move, let's say, forward and backward. So and so the rho I is the density of the mitochondria at some branch. So I, it's related to a dendrite of a neuron, and so you have a number I, and the the rho I is here is the density. Okay, and so it's given by this equation, but we look at stationary states. So you will say that the derivative with respect to the time is zero, and this is a transport equation. So the derivative with respect to time equals, so minus or plus, depending on the direction of the where the mitochondria is hitting. And then we have our parameter k, which this will slow down the movement, okay, because you have an exponential decay here, this term, and you have increase in the movement, okay. And then so plus means one direction, minus means the opposite directions, and you have also a stationary for the s, and this is given by this equation. So basically those are transport equations. So I myself, I didn't go much more in the paper, but that's a good interesting paper to study within within the topic of our lectures here.